So this is the viewpoint. If we look at it from the positive x-axis, like you are sitting on the arrow on the positive x-axis looking down at the region, this is what you would see. And just to give it a little bit more perspective, if you were to draw a line parallel to the x-axis and then you try to trace out where you're going to enter and exit the region, if you're at some point in the solid, you're going to be entering the region when x is equal to 0 and then exiting the region right around here. And that is the function that's described by the plane. But if you're at another point in your xz, you would be entering and exiting the region in two different places. And so what we need to do is we need to find their intersection. I think we found that last time. We found their intersection and then do those integrals separately. So I have another cool picture. This is the same picture without the arrows, but this time you can actually see the two different regions. Well, to make it really clear, there are the two different regions that you would be integrating. Pretty cool, huh? Whoa. So, if you look at it directly from the x-axis, you should be just seeing these shapes. And then if you look at it from different angles, you see the boundaries of those shapes being cylindrical in some form. Cylindrical in the sense that they're being swept along the x-axis. No, I just did it last night. So I can upload it up there, the new and improved versions. But were you able to download it? The graphing calculator program? Sort of. Okay, because I tried to download it and it didn't work, so I'll see if I can find a way to upload it. But anyways, what I did here, I just played some games here. I have these surfaces, and then I just added a vector to it that would move it away in the y direction, and so that's how it gets split up. I think this would be interesting if you guys can download this graphing calculator, file, and take a look at to see what the slider is about and what these parametric surfaces are about. And if you can understand it, great. And then you can change a few things and then see how it would change in your pictures. All right, so you didn't have to add on to your notes. We can go back to our problem that we were going to do. So here we have a triple integral, and our integrand is z. And remember that dv is the dx, dy, dz in any particular order that you need it to be. Bounded by a cylinder, y squared plus z squared is equal to 9. And the planes x is equal to 0, y is equal to 3x, and z is equal to 0. And they're all in the first octant. So it looks like our our cylinder is going to get cut up. So we have a regular circular cylinder, and this is going along the x-axis because this has just a y and a z. So this is your cylinder. The plane's x is equal to 0. That's the flat plane in the back. and then y is equal to 3x. Now y is equal to 3x does not have a z in it, so I probably want to look at that on the xy plane. And on the xy plane it might look something like this. So I would imagine that that's just a plane going up, slicing that. And z is equal to 0 is the that's all confusing. What? Yeah, I didn't use different colors. All right. So what I wanted to do is I wanted to show you that in a lot of cases we seem to be integrating with respect to z first, and this is probably one of those cases where we don't want to integrate with respect to z first. So let's see. Because of this cylinder that goes along the x-axis like this, I'm probably interested in having this x squared or y squared plus z squared is equal to 9 as a region on the yz plane that I'm going to work with my double integral. And so that probably means if my double integral, my two-dimensional region is going to be restricted on the yz plane, I would probably want to integrate with respect to x first. Okay? So, if I'm going to integrate with respect to x first, I have to imagine where this is going to go, what my region is going to look like. It's kind of hard to picture what my region is going to look like. But if I'm going to integrate with respect to x first, this cylinder will have nothing to do with this inner integral. And so I just kind of look to see where my x's might be involved here. And so it looks like I'm going to enter my region at x is equal to 0, and then I'll be inside of the region and eventually exit my region at x is equal to, what? 1/3 y, so I need it in terms of x. So x is equal to 0, and y, or x is equal to 1/3 y. That's where I'm going to get out. And then this is happening in the first octant, so I want the x, y, and z to be all positive. So if I draw the cylinder, I'm only going to need a piece of that cylinder over here. And then from here, I can decide whether to integrate with respect to y first or z first. And we can just pretend we're going to integrate with respect to z first, where our z is going to go from 0 to this piece of the circle, which is, kind of obtained from the cylinder. So z is equal to positive 9 minus y squared, all under square root. And then I integrate with respect to y, and my y limits are what? 0 to the square root of 9, which is the radius of that. Okay? All right, if you haven't gotten this picture yet, can you, for those people who are visually inclined, can you describe what this looks like? A wedge, almost like a wedge. What's up with that wedge?
Well, it's a quarter circle that's swept out just a little bit.
Yeah, so it's a wedge that if you yeah. It's a wedge that's cut in half. So this is this part right here when x is equal to 0, and this is this part over here. This is a piece of the plane when y is equal to x cubed. And then, so if you were to draw a line parallel to the x-axis, you would enter the region through the back here when x is equal to 0 and exit the region through the front here with this plane. And then a two-dimensional picture is just this stuff. All right, so we can just set up the integral. We don't have to compute it. Say it again. The red line is we're integrating with respect to x first. And so it's like parallel to the x-axis. I would be entering through the region when x is equal to 0. That's the back plane. And then this front plane over here is when x is equal to 1/3 x, or y is equal to 3x plane. Say that again? You can, but this is probably the easiest way to do it. So dx goes from 0 to y over 3. dz goes from 0 to the square root of 9 minus y squared. And the dy goes from 0 to 3. Okay, I think this is easy enough to integrate. You guys can deal with this. Okay. Let's do one more triple integral example. No, I don't want to do that one. Let's move on. What can be done? Say it again? Oh, well, we can make up a story. If z is your density function, if z is your density function, you're saying at some height z, the density is going to change. But if you fix your height, then the density is going to be the same for all that. So at some height z, as it's going up, that's your density function. And then if your shape looks like this half wedge, then you're essentially finding the mass of that wedge. Okay? All right. Let's do a simple example where we're finding a volume of a paraboloid. And I'm going to turn the paraboloid upside down. So I'll say z is equal to 1 minus x squared minus y squared. So I'm trying to make this kind of simple. Say we're trying to find the volume of a paraboloid. Z is equal to 1 minus x squared minus y squared. So this is an upside down paraboloid moved up by 1 unit. And you want it above the xy plane, so you just want that volume there. Remember that if you call this region the solid E, then the volume, let's just say VOL for volume of E, is going to equal to the triple integral of that volume, and the integrand is 1. So what we want to do is we want to describe the solid. And for us to describe the solid, to set up a triple integral, we want to integrate with respect to x, y, and z. We want to find inequalities. So what are we going to integrate with respect to first? What would make sense here? It would make sense to integrate with respect to z first. So if you draw a line parallel to the z-axis, you would enter the region when z is equal to what? Z is equal to 0, and when z is equal to, and then exit when z is equal to this paraboloid. And then after you do that, you look at the two-dimensional picture of the shadow that this is going to make on the, since we went through the z, we want the two-dimensional picture of the shadow on the xy plane, the other two variables. And you can kind of see what that is, right? That's just a circle. But what's the radius of that circle? It's usually the question. So how do we find this circle, the radius of that circle, where the paraboloid intersects the xy plane? Set z equal to 0, right? Because that's the xy plane. So if you set z is equal to 0, then you get x squared plus y squared is equal to 1. So if you're going to write this in as an integral where we would integrate with respect to y and x, we would set up a double integral that's described by the circle. And what is that going to look like? What? Well, we could use polar, but let's go through this process just to show you how much more work this is compared to polar coordinates. So if we're going to integrate with respect to y2 first, I would draw a line parallel to the y-axis, and I would enter my region through a couple of semicircles, the bottom semicircle and the top semicircle. Right, the bottom semicircle, if I solve for y here, I get y is equal to the square root of 1 minus x squared, but it's negative because that describes the bottom part. And then the top part would be the positive part. Okay? And then the limits for x, negative 1 to 1. Constants, right? So we can see that this integral is going to look like this complicated looking thing. So my integrand is 1. I'm going to integrate with respect to z first from 0 to 1 minus x squared minus y squared. And then I'll integrate with respect to y from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then I'll integrate with respect to z, with respect to x from minus 1 to 1. And we could probably use symmetry and all that stuff, but that might help a little bit. But, you know, we've seen problems like this before, at least with double integrals. We've seen problems where it would have been much easier if we went directly into polar coordinates. So there is a polar coordinates that we can use in 3 dimensions, and it's exactly the same as polar coordinates in 2 dimensions, except in 3 dimensions we want 3 variables. So the x, y, and z become r and theta, and then the z just goes up and down. So we want to essentially go to polar coordinates, but we want to be able to describe polar coordinates in 3 dimensions. And so what we have here is a relationship the same relationship that we've had in 2 dimensions, but then we have to account for a z component as well. So we just say z is not going to change. We'll just call it z. So this relationship is actually not polar coordinates anymore, since we're dealing with 3 dimensions. This is called cylindrical coordinates. And really, the difference is that we have a z, and it's equal to z. So it's the same as polar coordinates. Well, in polar coordinates, though, we went from dA to r dr d theta. So now we have to deal with, since this is cylindrical coordinates, we're in 3 dimensions. So we do have one more piece of business to talk about. And we don't have a dA anymore in 3 dimensions when we're doing triple integrals. Instead, we have a dv. And the dv is that dx, dy, dz in some permuted order. So we essentially want to bring this to 3 dimensions, and now our 3 variables are r, theta, and z. So we're going to need to be able to integrate with respect to r, with respect to theta, and with respect to z. So we have your dr, d theta, dz in some appropriate order, and then because of this Jacobian thing, the derivative, the differential, whatever we want to call it, it's the same as it was before. It's going to be r. And to actually figure out where this really comes from, if you really want to know, the differential comes from the derivative of the old variable with respect to the new variables. Right? That's kind of like how we did the trig substitution. So it's kind of strange the way they call it. Is the d of x, y, and z with respect to r, theta, and z. And if you remember back when we went to polar coordinates the first time, we had a 2 by 2 matrix. We had a dx, dr, dx, d theta, some stuff like that. So it's the same business over here. We want the partial of x with respect to r, the partial of x with respect to theta, partial of x with respect to z, partial of y with respect to r, partial of y with respect to theta, partial of y with respect to z, partial of z with respect to r, partial of z with respect to theta, partial of z with respect to z, since z is the same thing as z. So we're going to get the same business that we got last time. I don't know if you guys remember, but the partial of x with respect to r is just cosine theta. Partial of x with respect to theta is, what is it, negative r sine theta. And partial of x with respect to z, since there are no z's in there, is just going to be 0. So same, almost the same thing over here. And then the partial of x with respect to z, since there's no z's in there, and the partial of y with respect to z, those are both equal to 0, and then the partial of z with respect to z is 1. And so when you work this out, you'll have some sine squared plus cosine squared business that will cancel out. Do you remember what this was called? This is called a Jacobian, and this is the last section in this chapter. Again, they don't talk about this. They do this in some geometric way that would see how that rectangular box changes into a slice of a cylinder. But really, mathematically, there's this idea of a Jacobian that gives us the differential or the change in variables. Anyways, so that's where the R comes from. So that means if we redo that same problem that we were looking at, we could have gone directly into polar coordinates. So looking at our problem again, the idea is to describe this in polar coordinates. And so we'll see that when we describe this in polar coordinates, it's essentially going to be the same thing that we had, except for one minor change. When you draw a line parallel to the z-axis, you enter through the region that z is equal to 0, and you exit through that region when z is equal to 1 minus x squared plus y squared. But when we go to cylindrical coordinates, all the x squareds plus y squareds need to change into r squareds. So instead of 1 minus x squared minus y squared, you're going into r squared, 1 minus r squared. And then back to that circle that we had on the xy plane, if we knew that this is a circle of radius 1, instead of finding out the y is equal to square root of 1 minus x squared business, we can go directly into polar coordinates, where r goes from where to where? 0 to 1, and then theta goes all the way around from 0 to 2 pi. Okay? So the other thing that you need to take care of with a cylindrical coordinate transformation is that if there's anything else in the integrand that you need to change, you should change that as well. So in this case, it's just a constant 1, so we don't have to change anything. So we'll just leave it as a constant 1. And now we have our triple integral looking like this. So it's an integral of 1, and then the dv changes into r, and then we can decide what we want to integrate with respect to first. And looking at this, it looks like z is dependent on r, so I want to make sure I want to integrate with respect to z first before I integrate with respect to r. And with respect to theta, that doesn't matter which way it goes. Question?
So it's not like in the polar coordinates where it's better to do r before theta?
We're most likely going to be doing r before theta here for most cases, almost all the cases, except there's another variable z, and usually we want to do z first. So the z goes from 0 to 1 minus r squared, and then now we throw in the r going from 0 to 1, and then the theta going from 0 to 2 pi. Order of dr d theta doesn't matter. It doesn't. We don't necessarily have to have z go first, but usually they do go first. Because most of the time you'll have z as a function of r and or theta, and then usually we're we're restricted to doing circles and stuff like that. So that's usually a nice function, or nice constant limits for this. All right. So this is called cylindrical coordinates. Usually, when they have rectangular coordinates, the Cartesian coordinates are called rectangular coordinates, and you can usually tell the shape by having constant limits for your three variables. So if you had x, y, and z, and you had constant limits, what solid are you essentially looking at? How does a solid look like? A cube or some sort of rectangular box, right? If you had constant limits for this, what do you think you would have? So it's kind of all in the name, right? Let's just say I went from -1 to 2, and then my r were constant limits from 0 to 1, and then my theta were constant limits from 0 to, let's go with 2 pi for now. What is this going to look like? So this will look like a circular cylinder. My r goes from 0 to 1, my theta goes from 0 to 2 pi, so that goes all the way around. And my z goes from -1 to +2. So I would have a cylinder that went from z is equal to -1 to z is equal to +2, and then it would be a circle all the way around. So the idea behind this and why it's called cylindrical coordinates is that with constant limits, these are your basic building blocks for this solid. But you're not restricted to describing cylindrical coordinates, because the example that we just did was a parabola. So anything that has some sort of cylindrical type shape, then even a paraboloid like that, it still worked out okay. All right, let's take a look at some examples from the book. There's volumes between places and things like that. Let's do 15, 16, and whoops, 15, 16, and 17. So sketch a solid whose volume is given by the integrals. Let's do the first one. If this is kind of difficult to look at, looking at the integrals like this, it might be good to break it down into those set of inequalities that we've been using. I personally like that, looking at the set of inequalities, because it's harder to read the inequalities from here. I mean, you can certainly do it, but it's better if you write it out. So my innermost integral is my first integral, or what I call my first integral, and that's a z variable, and I'm taking my z is equal to 0 and z is equal to r squared. Now, it'd be good if you can understand what z is equal to r squared means. And I think if you have graphing calculator, you can just punch that in. Z is equal to r squared. You know what this is going to look like? Yeah, so r squared is the same as x squared plus y squared. So if you change it to x squared plus y squared, you're going to get that paraboloid. And now we have this paraboloid. Remember in polar coordinates we talked about the paraboloid having cut off by a plane instead of the paraboloid that had sticks on the corner? Like if I were to draw z equals x squared plus y squared. And that looks like a paraboloid that has these things because its domain is a rectangular domain. If you look at the domain, if you look at it from the top, you can, well, it's a rectangular domain, so it finds those values. But if you look at the polar coordinate or cylindrical coordinate function, then it's looking at the polar coordinate ranges from r and theta. All right, so our r goes from 0 to 2. And so this tells us that our paraboloid is probably going to have an r value of 2, which means the height, r is equal to 2, so r squared is going to go up to 4. So your height is probably going to be 4. And then theta goes from minus pi over 2 to positive pi over 2. So that's not our 0 to 2 pi anymore. What's that going to do with our paraboloid? Cut it in half. It's going to draw the half of it. Now, which half is it going to draw? How would you describe that? What? Right? The right half? The half along the positive x-axis. So what you could do to describe this is go back to 2 dimensions on the xy plane and imagine how this r and theta combo will look like. So the r and theta combo would be r is equal to 2, and then you're going to start at negative pi over 2 and end at positive pi over 2. So this is going to be the shadow of your solid, and then you're going to have your paraboloid. You're going to have your paraboloid. Let's see if we can draw this paraboloid. So this is my positive x-axis. That's a positive x-axis. This is a shadow that we're making. And so the paraboloid just goes up. And then I'll draw the shadow in a slightly different color here. So there's nothing on the other side of that. This is paraboloid that got cut off. Now, this is a solid, right? Because this describes a solid. So the paraboloid itself is a surface. It's a 2-dimensional surface. I want a 3-dimensional solid. So the question is, what is a solid? Is a solid in here or outside? It's inside this inside? It's what? Under the paraboloid. So is this under the paraboloid? No. So the actual paraboloid bit that we want is actually outside of the paraboloid. Because we want your z value to go from 0, and then you'll be inside of the region until you get out of the paraboloid on the top part. So it's actually the outside of the paraboloid, the shadow that it makes on the xy plane. Too bad I can't just turn this, huh? I could pretend to turn it. That's not going to work. So I just want the outside part of the paraboloid. The outside part of the paraboloid that goes underneath going towards the xy plane. What?
So
Well, yeah, I guess.
like It goes from outside to the tip, like the edge.
Right here, yeah. To the tip. But if I draw, this line that I drew is kind of like in the middle of the region, so I would get it from the bottom and I would get it from the other side.
The parabola.
Yeah. But the volume itself is underneath. So let's see if I can get a different point of view here. Never mind. All right, so that's your region. Good? By that? All right. I could draw it in the graphing calculator program if we have time. Let's try this one. Z goes from 0 to R. Z is equal to R. We'll need to know what that is. Some of you know what that is already. And this time my theta went first, not like it mattered because it doesn't really matter for this case. But theta goes from 0 to 2 pi, and R goes from 0 to 2. So again, if I just focus on my xy plane out of my R and theta, what is my shadow going to look like? Circle. A whole circle this time? So this is a whole circle this time, a radius 2. And then my z goes from 0 to R. Did you guys think about what z is equal to R looks like? A what? Cone. Right? So remember that R squared is equal to x squared plus y squared. So R by itself, if you take the square root of that, if you take the square root of that, then you have square root of x squared plus y squared, which is in fact a cone. So it looks like I have my whole cone this time. So now the question is it inside the cone or outside the cone? This is my shadow on the xy plane. It's outside again, right? By outside, I mean everything under here. Yeah, if it was, whoops. If it was a top, then it would be, your lower limit would be R, and then your upper limit would be something else. Probably a number bigger than 1, or, bigger than 0. Okay? So you need to be able to manipulate through these limits for cylindrical coordinates. All right, let's see if we can do a problem here. Number 17. So this time you have an integrand. Think about the integrand as a density function if you want, where E is a region that lies inside of the cylinder and between the planes. Oh, this is easy. All right, let's do it quickly. So you have a cylinder. X squared plus y squared is equal to 16. So this is a cylinder with radius, whatever the radius is, 4. And then z is equal to 5 would be your bottom limit, and z is equal to 4 will be your top limit. So because the solid itself is a cylinder, you should expect to have constant limits in your cylindrical coordinate setup. And that's exactly what we have. So let's set up our inequalities. Your z goes from -5 to +4. They're just planes. And then your r goes from, well, I'm kind of skipping over the step, but maybe you should make sure that you draw your two-dimensional shadow. And this just happens to be circle of radius 4. So your r goes from 0 to 4. And your theta goes all the way around to 2 pi. Okay? So you write your integral out, and the only thing left to do is to change your integrand, since your integrand is not a constant. You'd want to make sure you replace the x's with r cosine theta, the y's with r sine theta, and if in this case you have an x squared plus y squared, that's just going to be an r squared under square root. So having said that, don't forget that your dv is also carrying another r. And then you can write down your integral. So z goes from -5 to 4, r goes from 0 to 4, and theta goes from 0 to 2 pi. Okay. Questions? All right. Once you get the feel for cylindrical coordinates, all these problems will become easier for us to deal with. I didn't check earlier if there was a tricky problem here. And there's no. Is there a center of mass problem? Find the mass and the center of mass of the solid bounded by the paraboloid and the plane z is equal to a, where a is bigger than 0, where if s has a constant density. So they're calling it S instead of E. We've been calling it E. I'd prefer we call it E. So I'm going to change that to E's. Has a constant density, K. So that's your density function. So your rho is equal to K, constant density. So essentially what we're doing is we're finding the volume and then we're going to multiply it by K. That's to find the mass. All right, so what do we have here? We need to describe our solid. We can draw it out if we want. This is a paraboloid that's going up. And the 4 makes it wider or skinnier, I don't know. But the only thing I'm concerned about is how far is this going to go up and the shadow that it's going to make on the xy plane. And so I have a plane z is equal to a, some positive constant a, that's going to take this paraboloid and chop it off somewhere. And then its shadow is going to be what I'm interested in to find my polar coordinates. So when z is equal to a, I would just essentially solve for this. I get x squared plus y squared is equal to a over 4. And so if I want to find my radius, I would take the square root of that, square root of a over 2. So that is going to be, that's going to be my limits for r. And what that means is that if I look at the shadow on the xy plane, my radius is going to be square root of a over 2. Okay. All right, so let's find the mass. Mass is equal to the triple integral of your solid, and then the density function, which we found to be k. And so, I need to set up the integral. So my z, I'm integrating with respect to z first, and then my r and theta are going to be easy now that we figured it out. R goes from 0 to square root of a over 2, and theta goes from 0 to 2 pi. How about my z? Where does it go? Now, if it's 0 to a, remember, if you have constant limits all the way around, then you have a cylinder. We don't have a cylinder here, and the drawing got kind of messed up there because we did some other stuff, but I want the solid that's bounded by the paraboloid and the top. So if I were to draw a line parallel to the z-axis, I would enter through this region from where? The paraboloid, right? 4r squared. And then I will be inside of the region until I get out of my region when z is equal to what? Z is equal to a. Okay? Factor out of 4, x squared plus y squared is equal to r squared, 4r squared. So that's my integral. And let's go ahead and find our mass here. Our mass is going to be triple integral. The rho is a constant, capital K. And I went directly into polar coordinates, so my dv has an r in it. And then I'm deciding I want to integrate with respect to z first, from 4r squared to a. And then my r limits go from 0 to square root of a over 2. And then my theta goes from 0 to 2 pi. Why do I always? Okay. I suppose we should figure this out. Now you guys figure it out. So that's the mass. If I were asked to find the center of mass, I would need to find the center of mass. I would need a couple more integrals. But actually, I would need 3 more integrals to find the center of mass, technically speaking. But if you look at this with a constant density, and if you imagine how this thing is going to look like, what are 2 of my 3 values for my center of mass? 0. Which one's 0? So this here, if you look at this, is balanced, and it's centered at 0, 0, right? So I would venture to guess that my x bar is equal to 0 and my y bar is equal to 0. So we don't have to do those other integrals. Yeah?
So on the test, we can just write that due to symmetry?
Yeah. If you have a question like this on the test. So my z bar, this one I'm going to have to go through some computations. And so the formula is 1 over the mass, which we found already. Which you found already. Which you will eventually find, times, now we want the same triple integral over E, and then K, R, D, well, I'll just say dV. And then it's the density times the variable, right? So the variable here is Z, so we'll just tack on a Z over here and then multiply it by the density function. So use the same limits for your limits of integration, and then just go through and do this. By the way, let me just set up one of the x bars or y bars. Let's set up the x bar. So the x bar looks like this. Oh, do you? I don't think so. So it is x, right? All right. So in our integral, since we are integrating with respect to r and theta, since we're going to polar coordinates here, the z in cylindrical coordinates will remain a z. So that integral setup is fine by just replacing your dv and the limits. But for this one, you actually have to make sure that you're not integrating with respect to x or y here when you do your integral. So you need to make sure you change anything that has an x and a y into r and theta. So our integral here will end up being equal to 0 to 2 pi, 0 to square root of a over 2, 4 r squared to a. Now the k, or the k is constant, but the x has to change into polar coordinates, or cylindrical coordinates. So what should this be? R cosine theta. And k is at constant, and now your dv is going to be r dz dr d theta. Now this is one of those where you can break it up to 3 different integrals because well, you can't take the z out. Well, at least you could take the theta out. But if you integrate cosine theta from 0 to 2 pi, you're going to get 0. So that's why this is going to end up equaling to 0. But anyways, I just wanted to point this out because if you're going to change it to cylindrical coordinates, and we have r squared, or we have x squared plus y squared, that's easy to just change into r squared. But if we don't have x squared plus y squared, we just have like an x or like a y or e to the x or something like that, we have to consider that x as r cosine theta and then integrate that way. All right? Questions? Yeah. Oh, it's not a negative. It was an equal sign that got merged with a... Any other questions? Yeah.
Can you go back to the graphic? Sorry, forget that.
Which one?
The circle. You switch from open to
Rectangular?
from the oh.
Well, it's the same. It's the same surface. It's drawing out the same surface, except its domain. Its domain is a from the top view. Its domain is a rectangle, or in this case, a square. Well, yeah, if you're doing it that way, but if we're actually cutting it with like a top like this, then we would cut it with a top, and so those things wouldn't exist anymore. So z is equal to 4. If we would cut it from the top like that, those things will have to disappear. So you need to not look at it from a rectangular point of view, but from a... Okay. Anything else? I wonder if we can make this into a circle. No. All right. So this is cylindrical coordinates. There's one more coordinate system that we're going to study next time, and that's going to be based on spheres. So it turns out that cylinders and spheres are popular solids for us to examine. Can you guys think of any other interesting objects? What? So cylinders and spheres. Anything else like boxes or tetrahedrons, which is a pyramid of some type. Anything else can be described. We should be able to describe it using Cartesian coordinates. And so with the spherical and cylindrical coordinates, we just have an easier way to describe the volume, the solid.
We wouldn't have to do
And maybe I should throw the equations for the, yeah?
Do they have a system of coordinates for like theoretical dimensions?
Sure.
Sure.
Yeah, we'll find we'll find volumes of four-dimensional spheres and stuff. What? Well, you know, there's a circle, right? The circle, we can find the area of the circle, and then we can think of a circle as a two-dimensional sphere. So we find the area of a two-dimensional sphere. And then in 3 dimensions, we can find the volume of a 3-dimensional sphere. And then now we go up to the next level, we can, because we are using triple integrals already, it seemed natural that we should be able to find the volume of a 4-dimensional sphere. Except we probably wouldn't call it volume, we'd probably call it a hypervolume. Hypervolume of a 4-dimensional sphere. And then once we get that progression from the area of a circle to the volume of the sphere to the hypervolume of the 4-dimensional sphere, we could take it as far as we want. 5-dimensional spheres, 6-dimensional spheres. And we can get actual values for those things. And you know, we could take a look at these circles and spheres of radius 1. We could also take a look at a circles and spheres of radius, arbitrary radius A or something. Okay? And I usually say that as a problem on the test, but maybe we'll actually go over it in class, and I won't give it to you as a test problem. Maybe I'll give it to you as a special quiz.